Imagine that with just one click you can load a satellite image and identify streets, buildings, crops, and among other objects. Well, that has already been done, but why do it now? Team 66 has worked on a model to be able to identify precisely these objects, with the aim of being able to help the District Department of Economic Development to identify which areas of Bogota's rurality have productive units installed and where they could be located. And why is this important? Currently, there are no recent satellite images that allow knowing the rurality of Bogota to be able to create public policies to manage the resources available in the rural areas of Bogota. Comprehend how rurality works can help the 50,203 inhabitants of rural territory to improve their life quality, and thus develop the business culture in communities located in the countryside. Since the process of production, processing, storage, distribution, and marketing of supplies and agricultural products allow employment to those communities that are more vulnerable and are more remote from the city and its business center. On the other hand, the closest a production zone is to the distribution center, the better the results are in terms of cost and timing. In this case, it is needed to determine the areas of opportunity for the improvement of the rural territory to improve the competitiveness of the rural areas in Bogota through the strengthening of productive units and contributing to the continuous improvement, sustainability, and efficiency of the city's food supply system and the production models and technological capacity of Bogota's rurality.
So, how can we solve these issues? Well, we guide you with the solution with our artificially intelligent app that goes one step beyond. So let me explain you how it can detect what's on your satellite images and help you improve your policy making decisions. So let's give it a try. I'm gonna first upload my file image, and as you can see, it can only accept TIFF format. So I'm gonna open it, and this is really exciting. Our image is being processed by our AI. So I'm gonna see now the results, and as you can see, it takes very few seconds. Now let me explain you what's happening. Let's first start in our left side. As you can see, we see our main image and we see colored the classes that our model predicted. So for instance, we see that trees are green and we see all the green spots, trees, in our image. We can also, for example, deselect and we see no more the trees. We can also deselect buildings, deselect roads, and see with more detail what's happening in our image. We can also select back again all the buildings, all the roads, and we can zoom in our image and see in more detail what's happening in this area and what are the objects that it detected. So let's go back, and we can also see something very interesting, and we see the number of objects it detected. So for instance, it detected 37 buildings, as you can see, all distributed within our image, and everything that we can select and deselect back again. Finally, we can tell our model how strict it should be. So for instance, I'm gonna change the threshold of our model. I'm gonna say, let's say 0.8, and it's gonna bring less buildings and less trees. Why? Because it has to be 80% sure that these are real buildings inside of image. So as you can see, we can select many thresholds. And at the end, we can go back and try another image, making it a very useful AI application for everything that you need with satellite images.
In order to carry out our project, we have used some transfer learning algorithms and datasets obtained from external resources like DSTL's Satellite Image Feature Detection, which contains TIFF and shape files with geographical information and its attributes, which allows area recognition, image classification, and segmentation to label objects like buildings, crows, trees, crops, and among others, with the aim to train our model and predict which areas of Bogota are possibly suitable to install a productive unit.
Our proposed model is based on the UNet architecture. It was implemented and trained locally using TensorFlow 2.6 and Keras on a RTX 2060 QMax GPU for about 27 hours and a total of 300 epochs. An important metric for our project is the Jacquard similarity score, which is included in the scikit-learn library. Our model obtained a Jacquard coefficient of 0.48, which would position us in the second place of the DSTL competition of our main reference. The model is of convolutional autoencoder type. This is a diagram of our artificial neural networks architecture. The input for the model is an 8-channel .tiff format file, which is a tensor of 3 dimensions with the image's height, width, and the different spectral bands that are listed here in yellow. The input object can also be understood as 8 square matrices of 160 times 160 elements. The output is also a tensor of 3 dimensions with the image's height and width of pixels, and now the third dimension consists of 10 masks of polygons that represent the object classes detected by the model. The classes are listed here. The elements of the output matrices for each class represent the probability that the pixels of the original image correspond to that class. The model groups up neighboring pixels of the same class through a shapely polygon and finally creates a mask. What's shown in the image here is a superposition of masks displaying the classes detected in this case.
To get good predictions, the user may provide a TIFF file as an input on the front end. An error will pop up if a different format file is used in the submission attempt. The TIFF files must have a 160 by 160 pixels resolution and should contain the 8 spectral bands: red, red edge, coastal, blue, green, yellow, near IR1, and near IR2 to guarantee accurate results and be able to identify the objects for the 10 classes.
Our project is a stepping stone. In order to further develop a better understanding of the rural areas in Bogotá, some of the most forgotten parts of the district geography. By being able to identify productive lands, all of their components, and overseeing their development through the years only with satellite pictures, a cost-effective, quick, and precise method for data analysis emerges, from which it is expected that better and smarter public policies would derive, improved by a strengthened decision-making process that would now include a deeper understanding of what is going on, without the need of constant fieldwork for data collection. This is a project of great importance, since the citizens that live in these rural areas are some of the most vulnerable people in the district. They have been claiming for years for an improvement on their life conditions and for a transformation of the agricultural sector. This project would allow better coordination and planning, benefiting large and small producers equally, while simultaneously contributing to the continuous improvement, sustainability, and efficiency of the city's food supply system. This, of course, is not limited to Bogotá. The results are evidence of the model's applicability in nearly every context. Everyone who has an interest in understanding rural and even urban areas can do it from a data science perspective by using satellite images. And those that have the will and the abilities to affect these areas in a positive manner would benefit greatly from the project we developed. Thank you so much for your attention, and we hope that after this presentation you're as excited about all the possibilities and all the doors that are now open after this project as we are.